All right. Can everyone hear me well? All right, cool. So, hello everyone. As Pavel said, my name is Serapheim. I work at Delphix, and today I want to talk about our experience at Delphix debugging ZFS in Illumos and Linux. Just to give a quick background, as I said, I work at Delphix, and our product is basically an appliance that's powered by ZFS, and our customers run either on the public cloud or on-prem on top of a hypervisor. And we recently did this switch where we were using Illumos and we transitioned our operating system to Linux. And one of the main questions that was brought up during this transition was, can we maintain our existing debugging processes that we have from Illumos for issues that we encounter in production with Linux? As an engineering organization, one of our main goals on that aspect is to root cause on first failure. Whenever we hit an issue in production, we want to debug it there and then. For performance pathologies, what this looked like most of the time is hopping on the VM, gathering some logs, and if that's not enough, trace the system to analyze its runtime behavior. But for more severe issues like panics or deadlocks, what we generally do is we collect a crash dump and we do postmortem debugging, basically analyzing that crash dump in-house. In Illumos, everything was built with these use cases in mind, so our procedures were created accordingly. Now switching to Linux, many things carried over, but specifically for postmortem debugging, we found the workflows and the tools available not being exactly sufficient for our needs. So at this point, I'd like to take some time and talk about postmortem debugging in general, and specifically why is it so important for us at Delphix as an appliance company. Well, consider if we didn't have crash dump and we wouldn't do any postmortem debugging, and a customer VM crashes. The only state that you have, the only information that you have related to the failure is whatever the customer thought to mention at the time, whatever support thought to ask, and whatever logs were recorded while the VM was running that the developers thought during development that they would be useful. But most of the time, this is not enough for us to root cause issues. And if we didn't have crash dumps, what would end up happening is that we would iterate with a customer. And by iterating, I mean you would basically add some more logging statements or you change some code, give it to the customer run it, reproduce the issue, and then they come back to you with the new data. And then maybe you can root cause the issue, maybe you need to go through another iteration. And you can see where this is going. This is a very slow, it's a very error-prone process. And if you've done this iteration like 4 or 5 times, it can be a little bit embarrassing because it looks like you don't know what you're doing. So I don't want to say that crash dumps and postmortem debugging is a silver bullet. Sometimes you still need to do all the things that I mentioned, but a crash dump is comprehensive. Most of the time, it has all the state that you would ever need to root cause the issue, and it never lies. It's kind of like facts, not people's opinions. Another great point about crash dumps is that they decouple the activity of root causing the failure from the process of restoring the system. So if you look at the failure the first time, you see the message, you can kind of see like, oh, I can apply this workaround having taken a crash dump, and the customer can continue running their system while I root cause the failure on my own. I mean, this is a great thing. It basically lowers the severity of the issue right away. So I have a real-world example here, something that George and Matt worked, I think, 2 or 3 years ago. So basically what happens, like a customer hit an issue, and as an engineer handling the escalation, you see something like that. This is very similar to the message output that Tom showed earlier. So you're handling the escalation, and you want to start debugging the issue. So you look at the console, and you're seeing, okay, we are lucky, we hit an assertion failure, we get a nice output where it actually points out the file name and the line within that file name where the problem occurred. In this specific case, we see that the problem is in an assertion within ZIO done. So you start taking investigation notes, right? You're looking at the assertion, and basically what the assertion says is that the block pointer of that ZIO is not the same as the original block pointer, whatever that means for now, right? We're just looking at the code. Looking at the if condition, we see that, okay, this is a NOP-WRITE ZIO. whatever that means. And also an extra note is that this block pointer that the ZIO is trying to issue is not an embedded block pointer. All right, so what do all these things mean? What's a NOP-WRITE? A NOP-WRITE is a performance optimization that has potential savings for snapshots, space savings. Basically what happens is that ZFS compares the checksums of incoming blocks to ZFS and compares them to blocks on disk, to their destination blocks on disks. And if these checksums match, it means that nothing has changed. So we can actually skip doing that I/O. This is actually pretty common when you do full backups on large random access files that have almost identical data. So with that in mind, we basically rephrase the problem that we just saw. What happened? We are issuing a NOP-WRITE, but the block pointer that we are about to write, that we would be writing, is not the same as what's on disk. So that's basically a bug in the NOP-WRITE. Also, as an extra note, is that the block pointer is not an embedded block pointer. So straight off the bat, we can know that we can relieve the customer by disabling NOP-WRITEs right away. And here I have this one liner. Is basically we are passing a command to MDB that tells it to look up the ZFS NOP-WRITE enabled variable and write 0 to it, basically disabling that functionality. But before doing that, we also generate a crash dump so we can analyze it in-house. So, all right, so the system is running now, the customer is happy, but there's still this bug that other customers may be hitting. So we basically have two choices. We can start reading the tens of thousands of lines of related code, the ZIO code, the DMU code, you know, all the entrances to like the right code paths. Or we can start analyzing the crash time that we got and make targeted questions towards the root cause of the issue. So I really like this example because, you know, the ZIO code path is it's a little bit complex. George Wilson had a whole talk last year explaining all the pipeline stages of these things. And following the control flow just by reading the code is not very easy. The other thing about this is that looking at the stack trace, we can't tell where this ZIO came from. Basically, some kind of thread was spawned running ZIO execute right away, and it failed. What's even more interesting is that in the ZIO code path, many times, the thread that actually issued the ZIO may not be around anymore because this may be an asynchronous write. So even if you were to print all the stack traces in the system, you still, there's a possibility that you wouldn't be able to find the thread that actually issued the ZIO. So what I'm trying to say is that you need to inspect the actual data on the system, specifically the actual ZIO, see what it looks like. And there's no better place to do that than actually analyzing the crash dump. So what we would do in Illumos, we would start inspecting the ZIO. We would use MDB, the kernel debugger in Illumos that works on live systems and crash dumps. We would print the stacks with function arguments. And you know, we would look at the function, the first function argument of ZIO done. It's a ZIO T pointer. And we would actually print what the actual structure looks like. So in this case, what we're basically saying is that take that pointer, typecast it to a ZIO, and print it. One interesting thing about this is that IO done is set to debuff write override done, which means that this is a write override IO. And this is going to be helpful later. I just wanted to point out. But we can do cool things like examining what the block pointers look like. Now, I'm not going to go through like what these commands exactly mean, but I'm basically pointing out that the ZIO that we were about to write looks like this, the first image, and the second image shows what the block pointer on disk looks like. So these are obviously different, therefore, you know, it makes sense why the assertion was hit. But what's even more interesting is that the block pointer of disk is a whole, which means that the block pointer was freed. And when was it freed? We look at the birth time, and we see that it was freed at TXG 3891. Okay, that's kind of interesting. What's the current TXG? We can actually walk our way from the ZIO pointer all the way to the SPA structure, which basically describes the pool, and things like what's the currently seeking TXG. And we see that the currently seeking TXG is 3892. So basically that block was freed one txt before the current one. All right, so that's kind of interesting. So we are going back to IO done being set to debuff write overwrite done, which is basically a callback. And looking at the code, there's only one place where IO done is set to that, and that's debuff write. All right, so we're going somewhere. Looking at the code around this code path, we find a new clue. Basically, it's a comment telling us that this block was provided by OpenContext, and we came here either by DMU sync or DMU buff write embedded. So we have our two suspects where the ZIO could have potentially come from. But if you remember, we made that note earlier that that block pointer is not an embedded block pointer. So it must be DMU sync. So we look at the DMU sync code and we stumble upon this interesting part where there's this huge comment and an if case that potentially disables NOP-WRITEs. So reading the comment, what it basically says is that there's a possibility that our block may have been freed or its data may have been modified. So we should disable the NOP-WRITE because the context has changed. What's even more interesting, though, is that the if statement checks if the record has been dirtied, which means that it only checks if the data was modified. It doesn't check if the block has been freed. So lo and behold, that's our problem. So the actual fix would be something like this. And this is what ended up happening. Matt and George reproduced this in-house, and they came up with this fix. They basically added this extra case here in the if statement, and they restructured the comment to be explicit and say, hey, this could have been checked by being dirty, the first condition, or by being freed, then the second condition. So case closed. The problem was that we were issuing an NOP-WRITE, but the block pointer underneath us has actually changed. The root cause was that DMU sync wasn't doing good enough a job of considering if it should disable NOP-WRITEs or not. And the fix was adding the extra check. So just to do a recap, I hope that was motivating enough that postmortem debugging is like very important. It is, especially for us at Delphix. It allows you to examine the processor and in-memory state at the time of the crash. And what we've seen is that if you bundle it with a ZDB output, which is basically the corresponding on-disk state, most of the time is all the state that you need to debug a ZFS issue, on your own. And again, the great thing about it is that sometimes, as we saw in the example, we can decouple the activity of system recovery from the process of root cause analysis. And all these things are great, and crash dumps are very helpful, but there's no use of a crash dump if you don't have a tool that can analyze it efficiently. And we did some research on postmortem debuggers in Linux, and we found there was some work there, but we couldn't find anything that was sufficient enough for our needs. So we leveraged some existing projects, and we created SDB, the Slick debugger. SDB is a postmortem and live debugger. When I say live debugger, it means that you can attach it to a live system and you can introspect memory without actually halting the system. The system is still running. You don't want to just halt the system in production. Its user experience is similar to MDB. We basically drew from the lessons that we've learned by using MDB. And it provides basically a user interface where you can ask any questions by chaining a pipeline of commands together. And that should sound very familiar because it's basically a cell. And it can also be easily extended by Python. Developers can write new commands on it and just load them in the SDB runtime and run them. So I could go on about many hours talking about SDB, but this is the ZFS conference, and we're gonna look at some examples of debugging a ZFS with SDB. So very similar to what Tom showed earlier about the deduplicated stacks. Most of the time you want to see what's going on in the system. And keep in mind that all the command output that I'm going to show in this presentation works both for live systems and crash dumps. So again, you would say, okay, what's going on in the system? And you would use the stacks command. MDB folks should be familiar with that. bear with me for a little bit. You can see, for example, in this system, we have like 64 threads that are NFS servers waiting for something. And all the way down, all these things are sorted by count. We see some networking thread doing something. But we want to examine ZFS issues, so we can ask, okay, what's going on specifically for ZFS? So we say stacks-m ZFS. Basically, this says, show me all the stacks related to the ZFS module. So here we can see, okay, 17 threads are zethers waiting for something. We have 4 quiescing threads. We also have at the very end, let's say, the debuff evict thread doing something. And you can be even more specific from that. You can ask questions like, okay, are there any threads issuing any ZFS ioctals? And you can do that by writing something like this: stacks-c ZFS dev ioctal. Basically, you tell stacks, filter by all the threads that have this function in their stack trace. So in this example, we can see, okay, there's one ioctal doing a ser. There's another ioctal getting the history. There's another ioctal exporting some pool. But the real power of SDB is examining actual data structures. So in this example, let's say that we want to introspect pool state. Right? All the pools are part of this AVL tree called span namespace AVL. And what I have here is basically an SDB command that says, okay, I want you to examine whatever is at the address of span namespace AVL. And you can see the fields of the AVL struct. And what you would do in general with another debugger, if you wanted to, let's say, traverse this AVL tree and see all the data in it, you would basically start from the root, so you can pipe whatever you found into the member command, which dereferences a member out of a structure. Starting from the root, and then you can print out that root, and then you can go to the left child and then the right child one by one. But this is not very scalable if you have like 1 million nodes, right? So we have STB and we have pipes, so we can just make a command that walks it for us. And what's great about this is like definitely drawn from our experiences from MDB. On MDB, you would do something very similar, but you would say pipe walk AVL. Actually, STB, we don't just pipe integers and pointers around. We just pass like whole objects with their own state, like type information, addresses, values, symbol names, and things like that. So walk can actually figure out that, hey, I'm being passed an AVL tree, and I'm going to walk it appropriately. So in this case, we see that we have 4 nodes in our span namespace AVL, and we can cast these nodes to SPA-T structures, and lo and behold, we just, the output was humongous, so I just printed the first one. We have a pool name named application. We can get a pointer to its config, so far and so forth. We can actually continue our pipeline and print all the names of the pools by just walking the AVL, casting everything to a SPA-T structure, and dereferencing the SPA name member. And this is something that we've done so many times that we actually created a shorthand for it that also slightly starts printing things. So you have the addresses of the SPA-T structures on the left and their names on the right. What's also great about this shorthand, though, is that it's still a pipeable command, meaning that if it's not the last part of the SDB prompt and there's a pipe after it, it says, okay, they don't want me to print anything, so I'm just gonna keep passing my SPA-T structs over. So you can continue introspecting SPA-T structures just like that. In this example, I'm just printing all the syncing TXGs, the currently syncing TXGs of all these structures. But you say, okay, we have all these syncing TXGs, but that output is not that great. Like, what if I wanted to know specifically what's the current syncing TXG of the rpool? Well, these are just numbers here. Well, what you could do is you could actually use filter, and filter is a pretty powerful command. In this example, what filter does is, first of all, we take all the SPA-T structures and we filter all these objects that we are passed through the pipe, and we are saying, okay, I just want the objects whose SPA name equals to rpool, and then you can print the SPA syncing TXT. And again, we do this so often, so we actually added argument parsing to SPA, so we can do this right away, but filter by itself is just like a powerful command. And I have another example actually of how good filter is. Drawing from whatever we learned by Paul earlier about metaslabs and being loaded, let's say that we wanted to know how many metaslabs are currently loaded in the rpool. This would be a pipeline that we would construct, and we can walk this together. So these are the relevant C structures in the code. So what happens? We go through all the SPA-T structures and specifically look for the one whose SPA name is rpool. We dereference the SPA metaslabs by Flash member, which is an AVL tree. Then we walk that AVL tree basically all, which basically it's the AVL tree that contains all the metaslabs in the pool. We cast each node to a metaslab T pointer. And then we filter all of these structures by the MS loaded field, which basically indicates if a metaslab is loaded or not. And then we can pipe this to count, and that's basically like a pretty way of saying, okay, like how many objects were passed in this pipe. So that's pretty cool. We can basically ask almost any question that we want, and we can create a pipeline for this to answer our questions. For example, another thing, though, besides the pipelines, is also pretty printing. So let's say that you wanted to print all the unflushed allocation segments in the rpool. You construct a pipeline that's similar. You walk all the metaslabs, you cast them, and you get the MS unflushed allocations member, which is a range tree. And we have a command that you're passing it a range tree, and it pretty prints things. For example, okay, the first range tree didn't have any entries and 0 bytes in it, but the second range tree has 151 entries, and you can see them all printed nicely with their offsets and their lengths. And what's again cool about this is that range tree is not just a pretty printer. You can actually continue the pipe from there and say, okay, from these segments, how many are above this offset? So you use the filter command at the end, and you're saying, okay, I want RS start, range segment start, to be bigger than this value, and then you count them. So just focusing a little bit more on this concept of pretty printing, most debuggers, for something like a block pointer, here I dereference basically the block pointer of the overblock, would print something like this. This is pretty standard. We're like, okay, it's a C structure. I'm going to show you each field and the value of each one of the fields. And that's good. That's helpful sometimes. But most of the time, you have things like BLK prop, which is basically an integer where each bit is a flag. Or you have DVAs, divides virtual addresses, which here are represented with 2 uint64 each, but they actually mean so much more. So we have the block pointer command, which can basically teach SDB to make things more readable, decode these values for you, and actually present useful information that answers your question. So in this example, we decoded the DVA words to the actual DVAs here, and you can see, okay, DVA 0 is an address in VDEV0 at this offset with that length. Continuing on this example, BLK prop, as I said, it's like a bit field where now we can pretty print and say, okay, what all this big number means is that this is a level 0 block. We're using Fletcher 4 for checksumming. We're using LG4 for compression, and so far and so forth. Another very useful command that's currently a work in progress. This is the only sample that I could make working for now. Didn't have a lot of time before this presentation, but it is doable, is to ask the question on SDB, to ask SDB the question of whether is there any I/O currently on the system, specifically at ZFS, and we've developed the ZIO command where you can actually print all the ZIOs on the system. And again, this is This can be either for a running system or a crash dump. And this is pretty powerful because you can see the relations of all the ZIOs, parent to child. You can see what type of ZIO it is. You can see the current stage, and you can see if there's any waiter waiting on that ZIO. And yeah, continuing in this small tour of commands, when you hit issues about memory usage, sometimes you want to see, okay, like what do the SPL caches look like? So we created the SPL KMM caches command, where you get a nice report of all the caches and they're ordered by the top offenders. Basically, you can see here ZIO data buff has like the most active memory. But what's even more interesting is that you get a mapping of where the caches actually reside. In ZFS on Linux, for certain, depending on the size of the allocation, we do different things. For small allocations, we are using an underlying Linux slab cache. And for bigger ones, we use caches kind of like maintained on the SPL layer. So that's pretty useful to kind of like know and see where to look for different things. And specifically, with the Linux slab allocator, just doing merging, basically putting two different caches together sometimes just to like save space, you can be even more specific and say, okay, argbuff header T full is a cache that's backed by Linux lab, and it's actually part of the task stats Linux cache. And then just adding on top of this command, you can add more specific things like, okay, what's the memory usage of the B-tree leaves that kind of like Paul created. So what you do is like you use the SPL KMM caches command, you filter by the cache name, specifically you look for B-tree leaves, and then you pipe it back just to print it. So you see that, okay, it's using 316 kilobytes of memory. It's backed by a Linux slab cache named kmalloc 4096, whose total memory is 3.7 megabytes, and is utilizing basically 8% of that cache. And you can actually just break out of that and ask more questions. Okay, like what's the actual cache look like? And we have the slabs command, which is basically SPL KMM caches, but for the Linux kernel. And you can look up that cache and you can see, okay, the actual cache utilization is 65%. It's just that B-trees just take 8 out of these 65. All right. I have even more examples, and we can talk about them during questions and if we have time, but I just want to quickly go through how SDB actually works. You can't talk about SDB without talking about Dragon. Dragon is a small C library in Python developed by Omar Sandoval at Facebook. It basically enables the Python interpreter to introspect live systems and crash dumps. It comes with a nice Python API, an object model. It's pretty fast to start up. It still lacks some features like function arguments, but we're working on that. The community is still small, but they've started marketing pretty aggressively, and it's growing, and they're overall open to patches. So you could actually do a lot of these things that I just saw just with Dragon, as long as you are willing to just type on a Python REPL, just Python code. And this can be very cumbersome because, imagine that you're debugging an issue in production and you have the Python REPL in front of you. Like now, your focus should be debugging, but you're actually distracted by trying to write a program, getting your spaces right, and making sure that you don't get syntax errors. So, I mean, there is a reason why you use the cell for everyday things instead of like something like a Python REPL. So, okay, that's Dragon. What is SDB? SDB is basically a layer that leverages the Dragon API to provide the debugging experience that I just saw. It can be extended, as I said, in Python with new commands. These commands generally use the Dragon API to query whatever they need from the kernel. And then, this kind of like code that you can write to query the kernel can be reusable by using SDB constructs. So it can actually receive and pass objects through a pipe. And again, as I want to point out, like point 2 is a pretty powerful concept because we're just passing like Dragon objects that have like a whole context with them. They're not just pointers that we pass along. So just to recap, SDB is a debugger for live systems and crash dumps. It leverages the Dragon library to introspect its targets. It can be extended in Python to walk complex data structures that developers write, and things like filters and aggregators and pretim printers of data. And basically what we're going for here is that allowing the user to ask almost any question that can be answered given the available state that they have. Either this is a live a running system or a crash dump. And hopefully that's what makes it so great about debugging ZFS. I have other content, but at this point I would like to take any questions. Yes. Where does what? No, it's not. It's actually, oh, what? Yes, so the question was, where is this tool located and is it a work in progress? And yes, it is a work in progress, but we've already started using it and you can use it too. I have a resources page with a GitHub repo. It's currently under the Delphix GitHub group, but you should be able to clone it, work on it, and I'd be more than happy to accept patches too. All right. So the question was, basically, have we made any changes to ZFS to better support this tool? That's kind of like one question. And the second question is, in general, how do we handle ZFS changes in SDB? So to answer the first question, no, we haven't changed anything in the ZFS module specifically to support SDB. As for the actual changes of SDB catching up with whatever changes happen in the kernel, we currently do this by hand now. We are fairly stable. Like certain things like the SPA or the metaslabs, right, stay pretty constant, so we are safe for now. One discussion that I would actually like to bring up at some point is potentially having some SDB scripts decoupled outside of the SDB repo in ZFS. So ideally, when a developer introduces new code and adds new structures or made some changes, they also change the corresponding SDB Python scripts together with it. This is kind of like a model that we had at Delphix from before with Illumos and MDB, and it's something that has worked pretty well for us. And it also decreases the burden of like, hey, I need to maintain two different things in two different repos. It also, when you like submit a PR, at least me as a reviewer, it makes me a little bit more confident seeing that, hey, you've actually added some scripts together with your code. And if something fails in production and I have no idea about your feature, I can at least see what's wrong with like this SDB command that you provided. Other questions? Cody? Yes, so yeah, during our transition, we actually looked at a lot of different things. You could ask like, why didn't we just use GDB or Crash or something existing in Linux, or why did we not port MDB, right? And there are multiple trade-offs to all of these things, right? Specifically for MDB, it would be the porting effort is that it's pretty big, meaning that MDB, like even if we just ported it as it is out of the box, right? Currently, like it works with only with CTF. It has some DORF support, basically kind of like translating DORF to CTF on the fly while reading it. And I actually worked with Robert Mustaki to do that initially, but we had so many problems because CTF convert couldn't handle new DORF constructs after DORF version 2 and other weird things like that. So basically porting wouldn't be that easy. Now you could say, okay, like you already have this infrastructure, right? built on this. Like, don't you care about that too? But it turns out that once we found something like Dragon that does most of the stuff that we currently need, implementing a new interface on top of that is not a lot of engineering effort. And it actually works already with the Linux ecosystem, like, you know, the DORF symbol information everywhere, like the kind of like different types of crash dumps. Like, we wouldn't have to deal with writing that code anymore. And Dragon was something that was already used. So this basically, as I said, you know, like you could do everything. You could make GDB understand crash dumps, right? The question is, do you want to take up that work and maintain it forever just by yourself? Yeah, okay, yeah. Any other questions? George? All right. All right. So I just have a future work slide, and these are some of the things that we're thinking of doing in the future. I just wanted to point that out just for the GitHub repo here. There is as for the actual community, you can start by checking out the GitHub repo there, and you may actually find some references to something that we've started doing. Basically, we've created a small organization that we're trying to attract people working on Linux debugging across the Linux debugging landscape, meaning from debuggers to actual kernel developers, you know, changing the crash dump format and things like that. Unfortunately, I don't have a slide with all this information, but I'd be more than happy to share that with you. Yeah, we have monthly meetings, and we're basically trying to sync up all together to make sure that there's no duplicate work, you know, and you know, no two people are working on the same things, and kind of like, yeah, just basically do decision making on how we want things to look like in the future. All right. Oh yeah. First thing over there at future work is that we need more commands, ZFS, or even outside, if that's your jam. So I'll be there tomorrow at the hackathon, and I'd be more than happy to help everyone write new commands, or even just like set up SDB and use it to introspect the system.
All right, thank you, Serapheim, for this new great tool. We're gonna have a break now. Since we have one presentation less, we're gonna reconvene a little bit later, so we don't have 13 minutes for the break, but we have rather like 23. So let's reconvene at 4:10.